Hey everyone, I'm Siyuan, a fifth-year PhD student from UIUC.
Hi, I'm Jiyuan Zhang, a first-year PhD student from UIUC. Together, we will present our work, EMT and Operating System Framework for New Memory Translation Architectures. This is a joint work of the University of Illinois, University of Rhode Island, and CMU. In the past decades, the registry was the de facto translation design. Under this design, the page worker goes through the registry to fetch page table entries and perform address translations. Today, most commercial architectures use the radix design, including x86, ARM, RISC-V, and others. However, the registry table is known to have limitations, such as its performance and scalability. So in the past several years, people are actively exploring new translation designs. For example, hash table-based designs seen in Power and ECPT use hash functions to replace iterative tree work. On the other hand, some works, including DMT and ASAP, use a technique called direct mapping to perform translations. In recent years, we have seen many research works on these new designs, and in the future, there may be more new translation architectures emerging. However, despite many works have been proposed, few designs have been evaluated end-to-end with the operating system. There is a big question mark on their software applicability and implications. The root cause of this issue is that it is very difficult to implement a vastly different MMU architectures in the operating systems, as we will detail later in this presentation. And this difficulty already discourages disruptive architecture research, because they are too hard to implement and evaluate in commercial operating systems. We have already seen recent papers in architectural community that suggest focus on incremental changes. The key source of this limitation is the Linux kernel, whose memory management is hard-coded to a 5-level registry abstraction. Part of the reason is Torrellas believed tree was the only sane format. However, this assumption is no longer valid today. Let's take elastic cuckoo page table, or ECPT in short, as an example, which is a performant and disruptive hardware design that represents the class of parallel hash page tables. Here we show the differences on the right, and we use red for ECPT and blue for radix. First, instead of directly indexing PTEs with bits in virtual addresses, ECPT uses hash functions that need sorting and calculation. Second, in radix page table, PTEs recursively points to the next level in the tree, while ECPT always points to the actual pages. This breaks the assumption that the PTEs can be used to find other PTEs. And finally, ECPT works may give out multiple PTEs as candidates, which needs a filter to find the right one. However, for radix, no such filter is needed or assumed. While we only show 3 examples, we can already see that ECPT and other parallel hash page tables are not compatible with the radix abstraction that Linux uses. Hence, a question that we frequently hear from hardware researchers is, how can we make it easier to innovate in virtual memory? In this work, we provide an operating system solution. Specifically, we present EMT, an operating system framework for new memory translation architectures. It is a hardware-neutral design that bears no assumption on page table structures that applies to radix, hash, and mapping-based page tables and potential future designs. It exposes a clean, extensible interface that enables hardware-specific optimizations. Moreover, it also allows researchers to perform accurate performance profiling with near-zero performance overhead. We built an open platform based on EMT for memory translation research. It supports full system prototyping, development, and evaluation. We also open source DMT on GitHub. By leveraging EMT, we found new insights on translation designs from the OS perspective. We discovered new challenges from the software implications of hash-based designs, including ECPT. We proposed and tested new solutions to the challenges with our ECPT implementation and obtained new results. Now let's dive into EMT. In a typical system, the operating system kernel sits between the application and hardware. It is responsible for memory management. If we zoom in on the kernel, there are usually 3 parts of a memory management stack. First, we have the memory syscalls, which are the interfaces that the applications and the kernel use to communicate. Below that, we have memory management, which are the internal logic that perform actual jobs, such as page fault handling and swapping. And finally, there are architecture codes that translate the demands of software code into hardware-specific operations. However, due to the Linux design, many architectural assumptions are hard-coded in memory management and tightly coupled with architecture-specific codes, rendering adopting new designs like ECPT very difficult. To solve this problem, in EMT, we introduce a new abstraction and the corresponding interfaces to decouple these two parts, so that users can easily implement and replace the architecture parts without impacting the upper levels. Now, let's zoom in and see the abstraction we use to achieve this hardware neutrality. One key insight we use to design EMT is to model the functionality of memory translation rather than specific data structures. Specifically, we assume a paged memory, where each page is of any size, so we can support mixed page size settings like huge pages. Then, we assume these virtual pages are mapped to physical pages. Our observation is that each virtual page must have a deterministic translation outcome. Hence, we can abstract such an outcome as a translation object, which contains all the information about the mapping. Then, another observation we have is that each translation object can be uniquely indexed by the virtual address. Hence, we can abstract an entire address space into a database indexed by the virtual addresses. Specifically, the translation database tracks all the translation objects, as well as the hardware table and metadata which the high-memory hardware consumes. After we have the proper abstraction for page mappings and address spaces, we can finally abstract the MMU itself. The job of the translation service is to interface with the MMU hardware and also manage the lifetime of translation databases so that address spaces can be properly initialized and destroyed. This service also abstracts the functionality of address space switch and the MMU register context. Now, with the understanding of the abstraction, let me hand over to Siyuan for detailing the EMT design.
Thanks, Jiyuan, for the introductions. So the three basic abstractions become our EMT basic functions, and I will go through the operations that we support. First, for the translation object, we support operations like read and update the attributes of the translation object. The attributes include permissions and page size, etc. For translation database, we support operations like find the translation object, update it, or remove it from the translation database. For translation service, example operations are like switch to a translation database or get a currently running one. With the three basic abstractions and their operations, we have the basic functions of the EMT interface, and we call the implementation of the EMT interface a MMU driver. Different from memory translation architectures, have their corresponding MMU drivers. The basic functions are required to be implemented, and after it is implemented, we will get a functional and bootable kernels, and the basic functions are hardware neutral. However, they're not expressive enough to do hardware-specific optimizations. Thus, we introduced this group called customizable functions. They are hardware neutral and can also help us exploit hardware features. We have 7 groups of them, and here we list 2 examples which can help us iterate over or lock over a range of virtual address. So every customizable functions come with this generic default implementations that is hardware neutral and shared among all MMU drivers. However, if a MMU driver developer wishes to do hardware-specific optimizations, we can follow Linux convention to redirect it to the correct implementations. Here, we show an example of customizable function, which is the iterator group, and show it how it can enable hardware-specific optimizations. The iterator's job is to iterate over a range of virtual address and get the next translation object. Here we compare 2 implementations. The first one is the default implementations. The second one is the radix MMU driver. The default implementation is hardware neutral, but may be less performant when running on a radix tree architecture. The radix MMU driver is customized to exploit spatial localities. So for the default implementations, to guarantee hardware neutrality, every virtual address will go through a full page table walk on radix. And this has to be done even if two virtual addresses are right contiguous to each other. However, for the radix MMU driver implementation, if the virtual addresses are contiguous, and we can get the page table entries directly by incrementing the previous page table entry pointers. This way, we can exploit spatial locality of the radix tree design. Here we show a real snippet code. Let's start with the default implementations. We first find the translation object from the translation database, and this will involve a full page table walk. Next, we get the size, and then increment the virtual address by the size. For the radix MMU driver, we first update the object. If the virtual address are within 2 megabytes range, we can simply increment the virtual address and the page table entry pointers. And of course, we need to handle other cases. So with this example, we show that EMT customizable functions can enable hardware-specific optimizations. EMT simplifies the MMU support process, and with EMT, we only need to work on the MMU drivers. We need to start with the basic functions, and implement it will give us a functional kernels. Starting from the functional kernel, we can iteratively add customizable functions until we get a performant kernels. This iterative and development and testing process is very developer-friendly. So with this framework, we right now supports both tree-based and hash-based translations. For example, radix tree and ECPT. We also build support for flattening page table, which is an experimental design for tree-based designs. With EMT, the support is quite simple with less than 700 lines of code, and this is because we don't need to change the Linux memory management routines, and also we can reuse part of the x86 MMU driver. EMT has a negligible performance overhead. We compare the performance of EMT Linux on radix MMU driver with the vanilla Linux. And we tested over 3 suites of benchmarks. The first one is the kernel macro benchmarks. The second one is the macro benchmarks. And also we include 3 real-world applications. And for all of them, the overhead is controlled within 0.2%. The reason why is that EMT is carefully engineered. We follow Linux convention to minimize the call stack depths and keep a similar cache efficiency. What's more, EMT enables all the hardware-specific optimizations for a radix tree. EMT enabled us to build an open platform for virtual memory research. While evaluating new hardware MMU designs, we face the challenge that there's no hardware available to run software. So in our design, we have EMT Linux hosted by QEMU. We can implement the MMU driver and emulate the hardware translation process inside the QEMU. With this, we can run applications unmodified. If we wish to do performance analysis, QEMU can help us capture the instruction trees and the memory trees, feeding those trees into different backend simulators. For example, like an instruction analyzer, or a memory simulators, or even a full system simulator like Gem5 to do cycle-accurate analysis. EMT enables end-to-end full system evaluations in the absence of hardware, and also supports rich performance analysis. In our experience, using EMT to build OS support for hardware translation architecture is incredibly helpful to understand their implications from the OS perspectives. Here, we just pick one example of our findings, which is the self-reference paradox for hash page table. So the context here is like this. The kernel code is also mapped with some kernel PTEs. And while the kernel code is executing, the MMU will need to refer to the kernel PTEs for translations. However, the kernel PTEs may move due to hash collisions, which is a unique challenge for this hash page table. Thus, we require move PTE procedure inside the kernel code. And there are 2 ways to implement this. The first one is to do an invalidation before copy. However, while the move PTE procedure is executing, the MMU may lose their access to the invalidated PTE. Thus, the system may crash due to missing entries in the transient window. So this approach doesn't quite work. The second approach is to do copy before invalidations. However, this will lead to duplicated entries in the transient window as well, which is an undefined behavior for the hardware MMU. The root cause here is that there's no atomic updates at multiple locations. So what should we do? Our solution is to do copy before invalidations plus with some extension on the MMU logic. So here's what we do. We patch the MMU logic to handle duplicated entries if the mappings and permissions are the same. So during the process of moving a PTE, MMU can still refer to the kernel PTE, and after it is done, it will point to the correct one. EMT also helps us analyze MMU design trade-offs. Here we show a kernel instruction breakdown over 12 benchmarks on radix and ECPT. We put the kernel activities into 5 categories, and let's first see what's the behavior of radix. So not to a surprise, most of them are within the page fault handler. However, when it comes to ECPT, ECPT spends significantly more work inside the page fault handler. And based on this, we can make the conclusion that ECPT is faster than x86 radix on hardware metrics. However, it may incur more page fault handling overhead when compared with radix. And this is because of their complicated hashing mechanisms. And this takeaway is very hard to find without really implementing the OS with EMT. To conclude, we argue that operating system support is essential for memory translation designs. Understanding the OS implications for architecture designs is very beneficial. We strongly encourage researchers to experiment with modern operating systems. To facilitate memory translation research, we also argue that OS extensibility is crucial to foster more research. Based on this, we propose EMT, an operating system framework for new memory translation architectures, and also an EMT-based open platform for memory translation research. Thank you so much. We can take questions now.